So just a reminder, it's 75 minutes, so till 3:15.
Sounds good. Yeah, it's nice that there is a clock.
Yeah, I think there was a year we did not have the clock, and it was harder for the speakers. I went to the. I also did see Ben's parents. Oh, right. That's where we went to. Yeah. Did you already make lunch this morning? I went to dinner last night for the chalk art thing. It was like some chalk art. It was like pretty cool. I got pizza. I had leftovers, so I threw it. Oh, nice. Very cool. Yeah. This was oh yeah, it was like both days. You go on Saturday to like halfway done. So we can get started whenever you're ready.
Okay, yeah.
Okay. I'll go ahead and introduce you. All right, we're ready to get started for the afternoon session. So we're very happy to have Ana Maria Raclariu telling us about aspects of holography and asymptotically flat spacetimes. Ana.
Thank you very much, Oliver, for the introduction. It's a pleasure to be back in Boulder. My only other time here was as a student in 2017. So I had a great time. I hope everyone else, all of you, are enjoying the school and Boulder so far. I'm going to start with a disclaimer. I woke up at 4 a.m. this morning, and I might say the probability is quite high that I'm going to say some silly things or write some silly things. But I hope that everyone is going to be as awake as this morning and alert, and is going to you guys are going to help me out and point out any mistakes that I'm going to be making. So I hope there's not going to be a lot, but just in case. Okay, so, and I hope everyone can hear me. If you don't see what I'm writing, if anything is unclear, please shout out, and I will try to adjust accordingly. So the first, I'm going to start with quite an extended motivation to this, because I'm not expecting everyone to be familiar with the topic. So let me just start by asking, by trying to answer why one should bother with this topic. So there's going to be 2 points that I'm going to try to make. So the first one is quite ambitious and probably quite far-fetched. But one reason to care about this is that we'd like to understand quantum gravity. So I think if you ask different people, what they mean by quantum gravity, you are probably going to get different answers, which probably means that we don't really know what quantum gravity is. But conservative, hopefully, definition that most people would agree on is that this should be a theory of gravity valid at all scales that reduces to general relativity in the classical limit. Okay, so here, just to be very clear, what I mean by GR is basically data that's given by some manifold M equipped with a metric G. So I'm going to assume that this M is D plus 1 dimensional, I guess in line with Luca's lectures this morning. And So we can have something like this schematically. And this manifold is going to have, I'm going to assume just one boundary, but there can be multiple in principle. I'm going to call this dm, where the induced metric on the boundary is going to be called gamma. So G restricted to dm is gamma. And this metric G is a solution to Einstein's equations. So G mu nu is the Einstein tensor, and this should be equal up to a factor of G 8 pi G Newton that I'm going to absorb in the definition of the matter stress tensor. So these are the equations. We're going to unpack everything later on. Okay, so I'm sometimes going to call, so this boundary is a special case of a Cauchy slice that I'm going to call sigma. And I'm going to denote the normal to this boundary n. And in general, this normal can be time-like, space-like, or null, okay? But in the way I've drawn this picture, this n squared here is going to be plus or minus 1. We're going to discuss the null case in a moment. So, okay, yes? In this particular case, you can imagine, so the way I've drawn this thing, I can imagine slicing the space-time with surfaces of different radii. And then, yes, if you Cauchy slice in the sense that if I specify the data on the slice and then I evolve it with Einstein equations, I can determine the data on any other slice. Okay. So now, next, to try to understand quantum gravity, the first thing that one can do is to quantize, right? We have a classical theory, usually in quantum field theory, we quantize, and one can debate whether the quantization is unique or not, but probably also most people are going to agree that the path integral is the way to think about quantizing. So one possible quantization is given by the gravitational path integral. So what we mean by this, I guess Luca already explained this morning, but I'm going to give a little bit of different perspective. So what we mean by this is that we allow the metric G to fluctuate and integrate over equivalence classes of G, where two metrics are equivalent if they are related by a diffeomorphism. Okay, so formally, what we would write is a formula like this. So formally, we have some psi. I'm going to explain why I'm calling it psi in just a moment. This thing is going to be a function of the boundary metric gamma. And this is going to be given by an integral over all bulk metrics G inside the space-time with the boundary condition that G on the boundary is gamma. And then we have e to the I, and then the action on M plus possible Gibbons-Hawking boundary terms or other terms that may appear. So here, for simplicity, for now, I'm just going to assume we are in pure gravity, and we're also in Lorentzian signature. So the left-hand side of this equation is sometimes called the Wheeler-de Witt wave function. So that's why I'm calling it psi. And this may not seem so strange, because we know that in quantum field theory, path integrals compute states. Okay? So here we similarly encounter a state. And a few comments about this. At least in d greater than 3 dimensions, sorry, I guess I'm using the notation where m is d plus 1 dimensional, so I want to say d greater than 2. So bulk 3-dimensional, so greater than 3-dimensional bulks. This thing is quite hard to compute, okay? So so why is it hard? Well, first of all, most path integrals that we are computing in quantum field theory are Gaussian path integrals plus perturbations, right? So you can do the same thing here. You can maybe find the saddles, like we heard from Luca's talk in the morning, and then integrate over fluctuations around on-shell solutions to the equations of motion. But in principle, that's still perturbative. Sort of, you do this perturbatively, right? So can make some progress. But we also know, when you think about perturbation theory, we also know that gravity, well, as an effective field theory is totally fine. It's going to make sense below some scale, typically the Planck scale. But if we want to understand quantum gravity, we want to understand it at all scales. So at some point, this is going to break down, okay? Because we know that gravity is not normalizable, so this just means that at every order in perturbation theory, one is going to have to add more and more counter terms to cancel the UV divergences. Okay, but that's fine. So sorry, that's not fine. But one can maybe make a little bit of progress by actually considering, so that's one approach that one can take, but we should remember that in gravity, this wave function here actually is not, of course, one can just try to compute this explicitly, but one can also try to identify this wave function by solving some set of Schrödinger-like equations on the gravitational phase space that are known as the Wheeler-DeWitt equations. And these arise from the fact that in gravity, you expect to have constraints. So the second point is that this psi of sigma, psi sigma of g, sorry, of gamma, solves some constraint equations. So these are called Wheeler-DeWitt equations. So why do we have constraints? So let me first write them down. We have the Hamiltonian constraint, and we have the momentum constraints. So these are just the statements that the following operators, h and hi, have to annihilate the wave function. So these, roughly speaking, they arise from the fact that in the bulk, we have diffeomorphism invariance. So we just said that here we're only supposed to integrate over equivalence classes of metrics related by diffeomorphisms. So this h, I'm not going to derive these things, but they're standard formulas that are derived in general relativity textbooks, and they arise from an initial value formulation of general relativity, also known as 3+1 formulation. So roughly speaking, you take your space-time, you choose some notion of time, and you foliate it with some slices, sigma. So here I'm going to use this generalized version of sigma as a Cauchy slices foliating the space-time. And what this generator H does is to translate you in time. So you can think of as time evolution as, okay, taking Poisson bracket if you want, or commuting with this operator H. So H generates time translations, whereas these HIs, they move you along these slices. No, this is why I was saying that I'm using a generalized version of this, of sigma. Sorry about, okay. So, okay, and one can write them down explicitly. I'm not going to use this very much, but I will make reference to these equations later on. So H turns out to take the following form, just to get a bit more intuition. So I'm going to call n squared to be epsilon, and this equation is only going to make sense when epsilon is plus or minus 1, okay, as we said before. And we have 8 pi g Newton squared, and then we have this normal ordered product of the following operators. So pi hat ij, pi hat ji. So I'm going to use the summation convention all throughout, minus pi hat squared. So this where pi hat is just the trace of pi, divided by d minus 1, plus the Ricci scalar associated to gamma. So this is just for the slices, plus some term that depends on the cosmological constant. So e times d minus 1 divided by L squared, where L is the curvature radius of the spacetime. So what is pi here? So pi, just like in classical field theory, one can equip the slices sigma with a symplectic structure, and one can identify pairs of canonical variables. And here, the slices sigma, they have metric gamma, and there's going to be a variable that's conjugate to this metric gamma that we denote by pi ij. So more specifically, this pi ij is just defined to be 2 over square root of gamma d by d gamma ij. Okay? And so this is the Hamiltonian constraint, and we also have the momentum constraint, which is just covariant derivative with respect to the metric on the slices, pi hat j, pi hat, this should be j, ji. So, okay, so what do we have here? We have set, so I runs over the indices of the, over the d indices of the slices in the directions of the slices, right? So we have the equations and we have the Hamiltonian constraints. So it's a set of differential equations that are second order on the gravitational phase space, right? Because notice that this derivative, like gamma parametrizes the phase space, and in general, gamma is a function of some chosen coordinates x parametrizing the slice. Yeah.
What do you mean by the normal ordering here?
Yes, so the normal ordering let's see. Yeah, so I believe that so there's one way to think about this momentum operator, but there is another way to think about it. So the idea is that in quantum gravity, one is going to promote the metric gamma, right, to an operator. So when you do that, in principle, you should expect there to be normal ordering ambiguities. So we're going to come back to that question in a moment. We're going to see that we're going to promote the linearized, for example, metric on these slices to an operator. So this is how gravitons arise. So then you have these fields that one expands in modes, and then one promotes the coefficients to operators. So whenever you have, so because here we are seeing these quadratic terms in pi, you would expect there to be normal ordering ambiguities that one has to remove.
Okay, so this is a prescription in perturbation theory, right, then?
I don't know. So why are you saying it's in perturbation theory? I mean, these are exact equations that are implied by full diffeomorphism and full diffeomorphism invariance. Why are you saying?
The mode operators, those don't have any
I see. Let me get back to you about that. So the reference I'm using for these, well, as I said, these equations can be derived in the initial value formulation, but I've been basing this discussion on this paper by Laurent Friedel, which is has the following archive number.
Because the quadratic normal ordering is needed, you expect the operators to
When,
be divergent.
well, whenever you have a product of operators, there's going to be divergences at coincident points. So
certainly need some order. I'm just
yeah.
asking which particular.
Yeah, okay. I don't know. I actually don't think that he actually specifies that,
Okay.
but yeah. I can get back to you about that more. Yeah.
So why do we expect a condition integral for just pure GR with no extra field to make sense, like no but it would be on 3D? Like, is there any evidence for this?
Sorry, so here the point was that, I just talked a little bit about GR, but then we can try to quantize GR. And the way to go about that is to compute this path integral, right?
Yes, but what is the evidence that this makes sense, like beyond 3D, like with no extra field, just pure GR? Like?
Well, we don't have that. That was the point I was trying to make. I don't think we have any evidence that this makes sense. So this is exactly like, you can try to make sense in perturbation theory and remove, like divergences, whatever, like you would do by adding counter terms order by order. But one thing for sure, but then we also know that whatever, so here I'm just saying that the left-hand side, provided it's well-defined, it should, okay, we don't know whether it's well-defined or not, but if it is, then it should obey these differential equations in the same way as the Schrödinger wave function obeys the Schrödinger equation. And these equations, they come from diffeomorphism invariance. Yeah?
I'm a bit confused. So if n squared is positive, it means that the sigma is space-line? Is it timeline?
I'm working in the sigma. Sorry, I should have said that. So I'm working in mostly positive signature. If it's positive, then sigma would be space-like, and that would be the case. So I'm going to give examples. So in ADS-CFT, the boundary is definitely time-like, and you can treat that as a Cauchy slice, at least within certain, at least for a particular region in the bulk that is obtained from it by causal development in the radial direction. Yeah, great question. Yeah, other questions?
Can I ask, is it obvious that the solutions to these equations should be the path integral? Like I feel like these are two disconnected statements. I know that, but I've never understood why.
Well, yes, because I think so, because here you're integrating over equivalence classes of metrics where the equivalence relation is defined as, as I said, two metrics are equivalent if they are related by a diffeomorphism. So I think by construction, since those two equations are just a statement of diffeomorphism invariance, I think it's guaranteed that if you actually define it in that way, they should obey the equations.
But there is a specific form of exponential I to the action, right? Like I could put f of g.
But these equations do not have any g.
The g is integrated out. This thing is only a function of the metric on the boundary.
So the constraints on the side.
Yeah, okay, maybe.
But, okay, yes?
So, but in the path integral formulation, do we have to somehow pick a compatible factor ordering between the two for them to be equivalent? The path integral give us the choice of factor ordering for the constraints.
I am not sure about that.
So we have this general covariance, and there's the no dynamics zone constraint. Is the wave function the function of the whole spacetime?
You are asked, sorry, so
is
if,
psi a function of
yes.
the metric on only one slice or on the whole spacetime?
So yeah, it depends on what kind of boundary conditions you are imposing. So you can imagine specifying initial data on some slice. So in this 3+1 formulation, I can say specify initial data on some slice in space-time, and then I can compute the path integral by I can integrate over all possible metrics that take me from this slice to some other slice. So I'm just illustrating the most basic example where I only have one boundary and I'm imagining a sort of compact manifold. Yeah.
So how to evaluate at a specific time this wave function? On a specific
We will come back. Well, I can see examples. Sorry, these are all great questions, but I think, yeah, okay.
I'm just wondering, so the Wheeler-DeWitt equations, they're coming from just diffeomorphism invariance? Like, if for the action I put my favorite diffeomorphism invariant action,
Yeah.
I'd always get these Wheeler-DeWitt equations no matter what.
So you should think about, so you should think about these HI and the H very analogous to how you would think about the constraints in electromagnetism. And you can think about constraints in electromagnetism upon as first-class constraints, and they generate gauge transformations. So any observable in electromagnetism should be gauge invariant, and hence should commute with these constraints. So here it's just the same thing. So one can show that these H and HI actually generate diffeomorphisms in time and the spatial directions.
Okay.
So this object psi should be unobservable, so it should be diffeomorphism invariant, and this is all these equations entail or encode. Okay, so you can keep questions coming, but let's try to move on a little bit. So, so these Wheeler-DeWitt equations are second-order differential equations on the gravitational phase space. So here, we're going to discuss in very specific examples how to identify these phase spaces. But here, from what I said so far, they are parametrized by these metrics, by the metric on the boundary, or this, some particular on some sigma, and these conjugate variable that I'm calling pi ij. Yeah, and okay, in general, and actually we're going to see later on, there could be edge modes, that could be other things as well that one might have to enhance the phase space by. So you may think, okay, so what are these good for? Well, they're still pretty hard to solve. So I think maybe this approach has been, people have started to kind of like revisit it more recently. So it appeared that I'm going to write a reference soon, but I would say that maybe this approach might actually be helpful in trying to understand holography for all lambdas. I mean, as I said, they are very hard to solve, but they have given us some insights so far, especially in lower dimensions, where one can actually simplify these equations and they become basically more similar to Schrödinger equations that one can actually solve. So now, one thing that kind of one can see, well, actually, one cannot see directly from what I've written down, but another way to think about quantum gravity is through the ADS-CFT correspondence. So I want to connect this a little bit to these ideas of canonical gravity. So what ADS-CFT, well, there's many things that ADS-CFT does for us, but one of the things that it's supposed to do is to identify or really propose that actually this Wheeler-DeWitt wave function is in full quantum gravity, if provided that this object actually makes sense. This should be the same, so equal, to the partition function of a conformal field theory in one lower number of dimensions. So provided, so here, I'm assuming I'm evaluating this in ADS, where the boundary is taken to be the time-like boundary at infinity, and this right-hand side is the partition function of the conformal field theory, where, so in general, sorry, I should say that in the bulk one can have matter fields as well in general. So I'm going to denote them by collectively by phi, where this is the boundary value of other fields. And from the boundary, on the boundary, this partition function is supposed to be given by some path integral with sources turned on for operators, which coincide with the boundary values of the metric and the bulk fields, respectively. So this is also going to be a function of gamma and phi. But here, these are sources for operators, primary operators in the d-dimensional CFT. Now, one can ask, so this equation again is pretty hard to check. It's conjecture, okay, of ADS CFT. But one way to check that this equation makes sense in the context of ADS CFT is to ask, well, the left-hand side obeys the gravitational constraints. So what does that mean? So this means that the right-hand side should also obey the same constraints. And for CFTs, it's it so happens that the HIs, they just generate diffeomorphisms. So like the partition function of a CFT, it should be both diffeomorphism invariant in d dimensions, and it should also be Weil invariant, okay? So the diffeomorphism invariant is actually imposed directly through the HI constraint. And then one can imagine that maybe this H constraint imposes somehow Weil invariance, okay? So roughly speaking, HI of psi goes to diffeomorphism invariance of the CFTD, and this other guy, so I'm going to put question mark here. This should roughly correspond to Weil invariance. And there has been a recent sort of interest in sort of this problem through this proposal of Cauchy slice holography. So I guess one of the papers is, it's building sort of on this paper that I quoted before by Friedel. So this is 2204, 00591. So they explain there, what they do is to explain actually that the second equality is not exactly right. One actually has to improve. There is like a TT-bar deformation and the whole story related to that. I'm not, it's not the subject of these lectures, but I encourage you to look at that paper because it's quite interesting. But at least you can kind of see why one would expect such an equality to hold. Yeah.
So in the ADS CFT case, the boundary Hamiltonian is one of the HIs. It's like a time translation, which is like
Yeah, sorry. Here in the usual ADS CFT case, where you have a time-like boundary, again, the boundary is the H would implement a radial evolution. So it would implement evolution inside the bulk.
the boundary Hamiltonian is one of the HIs.
Yes, in that case would, yeah.
So just a quick follow-up. So these equations come from like the initial value formulation.
Yeah.
But this could just be not knowing, but I thought the initial value formulation, like you have to make sure the differential equations are like hyperbolic, and that only works if in Lorentzian signature only works if you pick a time-like direction. Why does this work?
It should work in any space-time region that's not necessarily caused, but related, like, yeah, sort of causally related to the region on this boundary. So in ADS CFT, there is sort of like this entanglement wedge and like the evolution, this radial evolution. So basically, like the solution is completely determined through radial evolution inside some diamond that spans into the bulk. But it's talked about. I encourage you to look at the, like, for example, this is discussed in great detail in this Friedel reference. Yeah. Yes.
So here sigma is the boundary of ADS, right?
Well, yes, because in this particular example now I'm restricting to ADS CFT and I'm trying to connect this to the discussion before. Yeah.
But then I'm confused because I think this H is give you the evolution in the direction orthogonal
This is what exactly what, yeah, that's exactly what I was saying. Yes. Yes, so H generates evolution in the radial direction. Okay, so, but the main point here that, like trying to make is that, so on the left-hand side, we have a state in the bulk. And on the right-hand side, this path integral should, like this partition function, should also prepare a state on the boundary, right? So really, this equation, what it tells us is that the bulk Hilbert space should be the same as the boundary Hilbert space. Yes?
Sorry, can you clarify the comment? So I thought H was deriving back translation from the bulk.
No, so in this particular example, I chose a particular direction in the bulk to foliate my space, slices of constant that direction would be such that such slices represent a foliation in the space-time. I could have, it was just for, I will see in a moment that I'm going to foliate my space-time with no slices in just a moment. In ADS-CFT, you can foliate it with time-like slices. But yeah, so H will be generating evolution in that direction. Yeah. Yes?
One more quick question. On the left, you have a wave function, and the wave function is a basis-dependent statement. This wave function should be understood as the overlap of two states. What are these states?
Yeah, so, well, here in this particular example that I gave, I only had one boundary. So the path, so I'm computing, so the path integral is only going to depend on my state on the boundary. But if you have two states, like you would have, for example, I don't know, in the Zitcher, you would have to specify, you would have to compute, it would compute some overlap between two states in general, where it would be specifying boundary conditions on the respective states.
But should I understand this wave function then as an overlap between a no boundary state and the state where
In this particular example, yes, yes. Sorry, I realized I forgot to repeat the questions. So there were a lot of questions. The last one was.
Most of it is very clear. Yeah.
Okay, so I hope from the answers should be clear what the questions were. But yeah. Okay, yes.
So if H didn't generate just a diff, like for example in the first example you gave, where there is time evolution, then I would naively at least expect the constraints to make it such that psi depends only on gauge invariant combinations of the variables. But now that you're looking at the Wheeler-DeWitt evolution being radial, if that's a diff, like can I expect any particular combination of gauge invariant quantities to pop out in the psi depend functionally on the fields in a gauge invariant combination, or any particular combination I can predict beforehand? Does that make sense?
Sorry, I don't think I caught all of that. But if you take a Euclidean path integral, like if you take Euclidean ADS and you have some boundary, sorry, so your question is, do you always expect the left-hand side to be diffeomorphism invariant?
Yeah.
I would think so, because from what we said before, the path integral should be diffeomorphism invariant, and hence.
Right, but then in this case where you picked a slice, so gamma lives on a slice,
Yes.
and then moving slices is a diff, you're sort of hardly gauge fixed, no?
Gauge fixed. So here I'm thinking about this psi as a function of just the boundary degrees of freedom. So, sorry, I'm confused. So at least in ADS-CFT, right, we do expect, the CFT is a theory that's diffeomorphism and what are conformal transformations? They are diffeomorphisms that can be undone by Weyl transformation. So we would expect, at least from, I mean, this is definitely ADS-CFT dictionary, right? And so we would expect definitely the right-hand side to be diff and Weyl invariant. And so if there is an object in the bulk that is, well, if the path integral, the bulk path integral is supposed to correspond to this, then it better also be, yeah. Okay, so I'm going to try to refer a little bit. I mean, this is supposed to be sort of like an invitation, and I'm not even making clear how any of this is related to flat space holography. Sorry, I should write this point that what this star equation tells us is that the bulk Hilbert space should be the same as the boundary Hilbert space in full quantum gravity, but some comments are in order. So as far as I know, the left-hand side by itself, for reasons that have been brought up by you guys, the left-hand side is a rarely studied, well, I mean, Luca is going to talk about some examples where we can actually compute semi-classically like this path integral, but in general, in full quantum gravity, I would say that, you know, it's really not accessible. You cannot really compute that. But one uses the power of ADS, like what the power of ADS-CFT is, if true, is that actually you can bypass that and compute some partition function in a conformal field theory or in a quantum field theory on a fixed background. And here you have much more control over this object. So you would hope that this, if ADS-CFT is true, that this would teach you something about non-perturbative quantum gravity. Yeah?
So just to make sure I find this correctly, my understanding is that this input boundary metric gamma is the one that lives in the asymptotic boundary, not the physical boundary. So unless you like fix the boundary cutoff, you're not really moving the asymptotic boundary.
So the question, the statement was that gamma is the metric on the boundary. The answer it is yes, and the metric on the boundary is supposed to be thought of as a source for the stress tensor in the CFT, in ADS-CFT.
No confusion about my question, because you don't change
So the metric on the boundary is indeed fixed, yes. Sorry if I, yeah.
Another question then, the diffeomorphism, we are restricting to diffeomorphism, that doesn't change this asymptotic boundary metric. So like there's no question ever to like say, what if the diffeomorphism changes the boundary metric? Because we are by defining we are only considering the diffeomorphisms that doesn't change the boundary metric.
Yeah, I think I understand your question, except for usually, I mean, in conformal field theory, we usually fix a background, but conformal transformations are you are still allowed. Like for example, in the state operator correspondence, you would be like a conformal transformation would be able to take you from, you know, like the sphere to the cylinder or whatever, and the two metrics would be related by a Weyl transformation, right? So they are diffeomorph. So in general, we have these conformal classes of metrics.
But they are global transformations.
They are, yes.
Yeah. That's my point.
Yeah. Oh, okay, sure. Okay. Yes.
When we are equating the CFT partition function to the gravitational path integral over the bulk, does it have to be Euclidean or Lorentzian? Like, if it's Euclidean, do you still expect it to satisfy?
Usually, well, in the example studied, usually it's Euclidean, I would say.
So then that's why I was a bit confused.
The Lorentzian CFTs and correspondingly Lorentzian ADS cases are much less understood, I would say. Yeah. Okay, so, but okay, let me try to move on a little bit. So okay, so the left-hand side is rarely studied in the literature, but it would be nice, you know, like it would be nice to understand both sides independently, and it would be nice if people studied maybe a bit more these Wheeler-DeWitt constraints and try to maybe develop methods to maybe sort of construct these wave functions in more general cases. Okay, and then So this was one comment, and then the other comment is that, so this now finally starts to touch onto the topic of the lectures, which is that this star equation is not actually formulated, or, you know, not exactly formulated or understood in spacetimes of that are asymptotically flat, so that have vanishing cosmological constant, or in spacetimes of positive cosmological constant. So the reason here is that, so for example, if one takes this case that's going to be of interest in these lectures, the normal, so the boundary in this case, the conformal boundary is a null surface, and so n squared is equal to 0, and there's a lot of problems that arise in this case. So one thing that one can try to understand here is how to do null quantization. And people have tried, but there are many questions related to that. Is it the same as the usual like quantization with you know, time-like slices? Are these two quantizations equivalent, and so on and so forth? Similarly, at positive cosmological constant. So another thing I should say is that in ADS-CFT, okay, the boundary is time-like, so one can think about it as supporting a standard quantum field theory, where the notion of time on the boundary coincides with the notion of time in the bulk. So unitary bulk evolution should correspond to unitary evolution on the boundary. But in flat space, we don't really have this luxury because the boundary is null. And quantum field theories defined on null surfaces are much more challenging to understand. But there has been some, maybe like some ideas in recent years of trying to define and understand such theories, and they go under the name of Carolian field theories. And we may have more to say about them later on. So since, yeah, so just to draw a picture. So this is the conformal diagram, so Penrose diagram for an asymptotically flat spacetime. The slices sigma are slices of constant time, and you can see here that, you know, the boundary here is a null surface, but it's also a Cauchy slice at the same time, so it's not really a time-like boundary. So it's hard. I mean, it's harder to understand like what would it mean to define a quantum field theory there. And in particular, this we're going to introduce this more later. So say at future null infinity, scri plus. There is a time coordinate, an affine coordinate along scri. It's this retarded time, the difference between usual Minkowski time and some radial coordinate. And but this time is not really the usual bulk standard time. So there are in other words, there are constraints on the boundary, which you wouldn't have if you were to do time evolution in a standard quantum field theory. So, okay, so this was the first motivation. And the second motivation, which is maybe a bit more, here it seems like I've just raised a bunch of puzzles, but maybe a more down-to-earth motivation is that maybe we should try to understand, or better understand, GR before venturing to understanding quantum gravity. And here, there is a very nice and large class of solutions to Einstein's equations with vanishing cosmological constant. So here, these are, you can say, okay, these are a bit more realistic than ADS spacetimes, or maybe a lot more so, because, you know, on astrophysical timescales, our universe, actually the cosmological constant is actually very small in general. So on astrophysical timescales, it should, like, its effects should not really matter. So. And usually I get asked, so what do you mean by astrophysical timescales? So in our universe, just to be very concrete, lambda is exactly 10 to the minus 52 inverse square meter. So cosmological effects kick in at the so-called Hubble length, which is approximately 10 to the 26 meters. So the Hubble length is just the speed of light divided by the Hubble constant. The Hubble constant just gives, basically, roughly speaking, gives you the rate at which the universe is accelerating. And so just to compare this scale to our galaxy, so our galaxy has a diameter of approximately 10 to the 21 meters. And so you see that if we want to understand physics within our galaxy, for example, the black hole at the center of our galaxy, Sagittarius A star, then cosmological effects won't play a role. And naively, sometimes people say, okay, for gravitational wave physics, the cosmological constant also doesn't play a role. But here you quickly realize maybe that's not exactly the case, because all of the gravitational wave events that we have seen so far actually come from black holes colliding outside of our galaxy. So now we may start being worried, like why is this relevant? But then you start thinking, like, but how do we actually compute the gravitational waveforms coming from a gravitational wave collision? And we do that mainly by doing numerical GR and then sort of extrapolating the waveform all the way to infinity. And numerical GR usually solves for the gravitational waves that come from the black hole in some region relatively close to the black hole, right? They don't compute, these computations are usually done around the black hole. And in those regimes, again, lambda is negligible. And then, okay, lensing and so on can be accounted later on in processing the data. So the point is that in the 60s, so Bondi, Vanderburg, Metzner, and Sachs, they set the foundations of studying gravitational waves from black hole collisions in the distance is not too far from them. So they set the foundations for what we now call 3+1 dimensional asymptotically flat spacetimes. So I'm going to denote that this is AFS. And really what they were doing was to study the radiation from isolated sources in space-time. So how does that work in practice? So in general, when we, so for a long time, so when Einstein's equations predicted this existence of gravitational waves, right, people were not sure whether they were actually observable, right? Like, there's this, they had to do some gauge fixing, and like, it wasn't clear whether these things, whether one can define them in a diffeomorphism invariant way. So of course, LIGO actually observed gravitational waves not too long ago. And roughly speaking, the way that works is like this. So again, I'm going to draw the Penrose diagram of an asymptotically flat spacetime. And you can imagine you have some kind of quadrupole moment that is localized around this r equal to 0 at some origin. So you have to choose a coordinate system. So one of the achievements of Bondi, Vanderburg, Metzner, and Sachs was to actually identify a particular gauge in which one can think or like speak about gravitational waves. Okay, so this is called the Bondi gauge. We're going to discuss this hopefully today, but not so sure. Yeah, so let's see. So then from here, as I said, if there is some kind of source of gravitational radiation, so just to remind everyone, the Penrose diagrams, they are useful because they preserve the causal structure of space-time. So gravitational waves propagate at the speed of light, so they would be propagating along lines at 45 degrees on these diagrams. And they would be hitting some point on the boundary here at scribe plus at some particular retarded time u. That's t minus r. So again, on this diagram, our constant surfaces look like this. So you can imagine there is a detector sitting approximately somewhere at some particular retarded time and recording gravitational waves. And gravitational waves, as you know from general relativity, they are given by transverse traceless components of the metric. So H perp trace free. And they, just similar to the electromagnetic field, they go at as 1 over r in this particular coordinate system. And then they usually have two components, two contributions from two polarizations. And I'm going to denote these by C. Sorry, and I should say that pairs of points on this diagram are two spheres. And I'm going to parameterize these two spheres by angles, by a pair of angles, collectively denoted by omega. So we have one polarization, and then we have another polarization. And you may see, sorry, bar. So I don't have any indices here, and the reason for that is that usually, so here we have a detector, and the detector is associated with a frame, right? There is a frame of reference associated to the detector, and the left-hand side here is the projection of the metric onto that frame. So that thing is Lorentz invariant, but it will transform under the rotation of that frame. So this is really E1 mu, E2 nu, projected onto H mu nu, where these are frame fields. Okay, so then I should say here there's two polarizations. Okay, and everyone should be familiar with the pattern that one expects to get. Oh, it's pretty hard. To get from these gravitational waves. So sorry, I should say that the radiation is actually encoded in the time derivative of this metric component, actually, right? So if there is an non-trivial, so this goes under the name of the News tensor. And so let's consider, I'm going to focus on one of the polarizations. So on C component, I'm going to define the following quantity, n of u omega at some particular angle, omega 0, defined as the derivative with respect to the retarded time of C. And what LIGO observed was essentially a profile that looks like this. So on the x-axis, we have time, so here u, and on the y-axis, we have n, right? So this is like the strain, right? And so everyone has seen this pattern, so it looks something like this, right? So, and of course, this signal, it encodes, one can solve Einstein's equations to relate the transverse traceless component of the metric to the stress tensor of the matter, the quadrupole moment of the matter that generates it. So, okay, this is all just classical GR. So, what does this? So, how can this possibly tell us or anything about even semi-classical gravity, if you want. Not to mention quantum gravity. And here, to kind of address this question, one can, first of all, consider the Fourier transform of n, of this function n of u. So I'm going to suppress this dependence on these angular directions. I'm going to assume that there's going to be a gravitational wave that hits the detector at a particular pair of angles. I mean, it's secretly there, but I'm just going to focus on the time dependence. Yes?
Sorry, before we proceed, just to understand why we introduce more H and N. So are we supposed to think about this H and N to replace the data we specify in the ADS-CFT case as the boundary?
Exactly. We will go there as the lecture progresses. So you should keep in mind. So usually people, I usually give some motivation that sort of doesn't have anything to do with the lectures. But today, for these lectures, I decided to give a motivation that actually, like everything most of the things I've talked about so far will encounter them in some form or another later on in the lectures. So indeed, this new tensor is going to feature. I'm going to set things up in such a way that you'll see. Hopefully, by the end of the lectures, you'll see why I did this. Yeah. So the Fourier transform of n of u. OK, this is a very simple thing. Everyone knows how to take the Fourier transform. So it's just n tilde of omega. And it's just the integral over du from minus infinity to infinity. And it can be something like e to the I omega u, plus or minus. It doesn't matter. And I'm actually choosing the plus sign because I want to pick out the positive frequency modes of nu at scri plus. So here I'm choosing the sign. I'm taking omega to be positive. So the reason I'm doing this is that this will be a positive frequency mode at scri plus. OK. So now what does this have to do with quantization? So the thing is that in field theory, right, we usually expand fields in Fourier modes and we promote the coefficients to operators. And the modes here are exactly the Fourier transforms of these fields. So in quantum gravity, we would be promoting these n tildes to operators. And just for this particular definition that I've given, this operator would just be like a creation operator of at scri plus. So it would be creating a positive frequency mode of this new tensor in the outgoing state. Or equivalently, it would be creating an outgoing graviton. So in the quantum theory, we promote n tilde omega to an operator that creates positive energy graviton. In the out state. I can pick out the one for the in state as well, or I can also pick for the in state. So here by construction, I have n that depends on the retarded time. So by construction, this thing is going to pick out an outgoing mode. So the question is whether I have a plus or minus sign is just the plus sign will pick out a of omega that acts on the out state from the left, whereas the other sign will pick up an a dagger omega that acts on the out state on the left. So I'm going to write down in just a moment. So in general, quantum gravity observables include, so I'm not claiming that these are the only ones, but they should include, hopefully, scattering amplitudes that are defined as overlaps between in and out states. So here the out state, so I think we're going to hear more about this, who knows, maybe from Sebastian's lectures, maybe from Sasha's lectures later on. So out state is obtained from some given in state, some other in prime, by evolution with some hopefully unitary operator, namely the S matrix. And so if one specifies all of these matrix elements, one would, that would be equivalent to actually specifying the S matrix. And again, this is a very hard problem, right? It's just amounts to computing the path integral before, roughly speaking, with also insertions, right? So, so in particular, what is this out state? So this out state is proportional to, so let's assume we are only scattering gravitons, but of course in general we're going to have matter as well. So for gravitons we'd be acting on some vacuum defined such that it's annihilated by all of the annihilation operators. And then we'd be acting on this with collections of these n hats, right? Omega 1, n hat, omega n, right? This would be an n graviton state. But these n hats can also be related using all of the things I've said here. They can be related to the incoming ones via conjugation with the S matrix. So I can also write this 0 and then S dagger acting on n hat in omega 1 S S dagger dot 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 all the other guys, and then sorry S and then dot 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 S dagger n hat in S. And now you see that inside here, basically this S dagger, assuming S dagger is 1, this can be related to basically the out state created by acting with n ins here up to this S matrix. Yeah. Okay, the way I've written it, maybe this should be S's and this should be S daggers, such that on the out state I end up with an S dagger. But let me just, to be consistent with this formula I've written there, I think this should probably look like this. Okay, so here I want to make the point that actually if you are computing, so if you are able to measure somehow correlation functions or scattering amplitudes that are functions of these n hats in the outgoing state, that actually does contain some information about the S matrix, right? Because you can imagine preparing some initial state that's given, and then if I'm able to measure the out state, that's going to know about the S matrix. Okay? Yes? Yes, that is correct.
Could you repeat the question?
Yeah, so the question is whether the in and the out states are the same Hilbert space. Usually in quantum field theory, well, we are going to see that in gravity because of asymptotic symmetries. Actually, one might think that the two Hilbert spaces are not the same because there is the supertranslation ambiguity. But actually, the matching condition ensures that, you know, like it ensures that given an in state, if you evolve with the S matrix, or we hope it does, it ensures that you know, given an in state, if you evolve with an S matrix that's unitary, then the out state is going to be fully determined. So S provides a map between the in and the out Hilbert spaces, and then they should be related. But then we know that the S matrix has infrared divergences in gravity, so that's another can of worms or whatever. So it's not fully understood. Yeah. Yeah, that's a very interesting topic, and somehow I decided not to talk about that, but we can discuss maybe that later. Yeah.
So why is n hat creating a asymptotic single graviton state? I don't see. You use promote function to operate. How do you guarantee?
Yeah, so we're going to come back to that later. But if you think, so NU here is just the classical field. And I can imagine expanding that in Fourier modes. So take linear combinations of, by definition, right, of n tilde of omega e to the I omega u plus complex conjugate. And then when you quantize, you basically promote these n hats that are the coefficients to operators. Does that, sorry, I'm not seeing. It make sense? OK. Yes? We are going to come back to that. I mean, yeah, indeed. I mean, a massive particle you're asking. We will come back to that later. But roughly speaking, OK, here if you have like some massive operator, there's still going to be. I mean, one of the points that I maybe didn't manage to make here is that the in and the out states are usually, sorry, the in state is usually assumed to be a free state, and then it should be on shell. And whether it's massive or massless, it doesn't make that much of a difference. You just have to impose either q squared is equal to 0 for massless, or in which case, so like it is the case for gravitons, so you have things parametrized by an energy and two angles, but you can have massive particles that are parametrized by points on some particular hyperboloid in Minkowski space. I might say, I will say some things about this later on. OK, so so the point, yeah, so the point, yes, that's OK. So what I want to say here is that, so one thing, yeah, so n tilde is S dagger, sorry, S n in S dagger. So this guy actually knows about S in principle. Yeah, so I'm saying in principle because, yeah, OK, if I was able to compute these correlators, then I would know basically everything, at least about, say, pure gravity. But we are not able to do that. So how do we make some progress? So one can either expand, so again, perturbation theory. And one can expand in G Newton. So really, one has to identify a dimensionless parameter. But here, you know, like G Newton treated as constant, roughly speaking, you can expand in G Newton. So this is standard perturbation theory. Or, so there are many, in principle, one can make progress by identifying some small dimensionless parameter. So another option would be to say expand at small energies. So in Simon's lectures, we've also seen some other expansion of large impact parameter. So those two are actually related. So in some sense, he also talked about soft gravitons. But yeah, so another thing that you can do is expand at small omega I. So again, this is dimensionful thing. So you have to specify small with respect to what. But OK, let's ignore these subtleties for now. And one point I want to make is that the latter expansion may include, and we're going to see this later on, higher order terms in G Newtons, right? It's not a one-to-one correspondence. If I expand at small omega, it doesn't mean order by order in small omega. I'm also going to get order by order in G Newton, right? So this may include higher order terms in G Newton. OK, so let's now focus. I have a few minutes. So let's focus on the small omega expansion. And let's look at some features of that we're going to come back to later. So at small omega, this n tilde of omega. So now I'm treating this as a classical field. So you can, as some expectation value of this operator n omega in some state or whatever. This is going to be a function now, not necessarily a classical field. It's going to be a function of omega. And I can expand this at small omega. So I can take the sum from n equal to 0 to infinity of some coefficients that I'm going to call mn omega to the n. So you may wonder, well, why does my expansion start at omega equal to 0? And it turns out that that's an implication of the Weinberg-Soft theorem. So you may think, OK, Weinberg, that has a pole. Why don't I start at 1 over omega? But the pole is not in N, but it's in C. And N and C are actually related. So N tilde is related to C tilde by a factor of omega, because remember, U was time derivative of C. So the pole, this one has a Weinberg pole. OK, so this expansion makes sense. And the point is that, so here there is maybe a little bit of a surprising fact, but it is a fact. And it was, well, it's known to Ramanujan. So it's one of his theorems. Maybe now they seem like simple things, but so it says that given the Fourier of a function, f of omega, that belongs to the Schwartz space. So the Schwartz space is just a formal way to specifying functions that decay sufficiently fast, that are localized in omega. So both f and all of its derivatives with respect to omega fall off as you take omega to infinity. So I'm not going to dwell too much on that. So OK, Schwartz space. So given such an f, which admits an expansion like this above, so f of omega is sum from n equal to 0 to infinity, f of n minus omega to the n divided by n factorial. It's just the n factorial is just for simplicity. You can always reabsorb that in the definition of f. It's Mellin transform. So how is this Mellin transform is defined by its particular integral transform with respect to omega. So I'm going to call this fm of delta is defined as the integral from 0 to infinity, the omega to the delta minus 1 of f of omega is given by gamma of delta times this f analytically continued and evaluated at the negative delta. So I'm not going to prove this. There is a reference for this. Sorry, this is really, the reference is just the Ramanujan Wikipedia, for example. So, but you review one proof of this, for example, in this paper. Sorry, before questions, let me just try to wrap up. So, so the point is that this function f of delta actually is completely determined by these coefficients in the Mellin expansion. And furthermore, as one can check in simple examples, if I actually, so say I have this new tensor, if I specify all of the coefficients here, sorry, one thing I wanted to say is that if the Fourier transform is in the Schwartz space, also also the Fourier transform of this, so namely n of u, that would also be in the Schwartz space. That would also admit a Taylor expansion. So in principle, one can imagine expanding the gravitational wave in powers of u. And it turns out, it might seem a little surprising because we are expecting that Taylor expansions may only, so if I look here, if I expand around omega to 0, I would expect to maybe just recover a little bit here up to where this function turns the other way. But that turns out not to be the case. I mean, sort of an implication of that theorem is that if I add sufficiently many terms in the subleading expansion in omega, I can recover the signal to arbitrary precision over a larger and larger range of u. So these things are going to come up later. And so I guess I'm out of time. So thank you.
Thank you, Anna. In light of the time, let's have questions during the break, and we'll see you back at 3:45.
Yes. Yes. That's a good question. I think there are some assumptions. One has to input, for this theorem to work, one has to input some assumptions on this function f of n. So I think those assumptions might be equivalent to those functions having a unique analytic continuation. But I'd have to check that. There are some constraints on this f n for the theorem to hold.
Do those constraints work from the fact that increasing this space?
As far as I think it's an addition. I think there is an additional constraint that one has to specify, in addition to this thing being in the Schwarz space. I think there might be an addition. I come back to you. Yes, sounds good.
I just want to make sure that if I understand this correctly, but you're thinking of the n in and out, you can think of as being defined on the past and the future no infinity.
Yes.
Yeah, this is just like if you're considering, it's like, yeah, the reason for this is that they're like massive, like citations, right? But if it's massive, I suppose you have to define them on like timeline.
So here I'm just talking about gravitons, so massless particles.
Okay.
Yeah, you're totally right. For massive particles, there is a different story, and we will discuss that later. But most of these lectures are going to focus on gravity and actually pure gravity. So I think, as I said, you should keep in mind these things because I'm not going to focus that much on the massive case.
Okay. So
Yeah.
I mean, if you have massive particles, probably you also need to take that like the timeline past infinity and future infinity into consideration.
That absolutely. That's definitely the case. Yes.
Thank you.
Yeah, you're welcome.
I just wanted to clarify, the C twiddle you put at the end that was really the end to it. That was the Fourier transform of the
The
C
C.
component.
Correct. Yeah,
Perfect.
that's
Just
right.
making sure.
Yeah.
Thank you.
By definition, I have to include all
So you're saying that this would contribute out to like anything that's
So this will solve Wheeler-DeWitt equation.
Why? I love the
Because
first
this is
part in
this is what
particular. Like,
Wheeler-DeWitt equation is telling
yeah, I
us
feel
that
like
you're
I've
imposing
heard
the
the
things
words
that
like Wheeler-DeWitt like 100 times, but never seen
diffeomorphic, and this is invariant.
Yeah, that was great.
This will automatically
Yeah,
solve.
there
But
were
it's
too many.
just like you were saying, right? There's
Yeah,
you're integrating.
Yeah, that's good because like Wheeler-DeWitt is such like
Yeah, but
and like
but I'm saying any F will do
but I
that.
think it only
Any
applies to,
gradient,
like,
any
what I
different
want
them invariant then do.
like what I don't do.
But now
Anything which integrates
yeah.
Hi, I'm also on it.
Hi, nice to
Why
meet you.
would it
Do you? I'm part of like the amplitude scaling debate. So I hear people talk about the Millen transform. Why is that
so
the
I didn't
object
miss
of
anything.
not
Yeah, we're going to talk about that, but roughly speaking is like what this Mellon transform does when you talk about asymptotic, like these asymptotic particles, like free particles in the cosmic space, is that it implements a change of basis from momentum basis to a boost basis.
Yeah,
This boost basis
I think one
is
bit this way is fine. This side is